This is the second video about partial fraction decomposition, and in this video we're going to go into more cases of partial fractions than we saw in the previous video. And we're going to base ourselves on three results, two of which are written here, and the third one will come a little bit later. So the first result is that if we have q of x, if q of x is a polynomial with real coefficients, then q of x can be factored always into a product of linear and irreducible quadratic factors. Right? So we are thinking about q of x being the denominator of our rational function that we want to anti-differentiate. And so that rational function, that denominator, that q of x, can be factored into linear and irreducible quadratic factors. The irreducible quadratic, remember, we said has discriminant delta, which is b squared minus 4ac, which is negative, That was a little bit of a brain stutter there, which is negative. So the second thing that we are going to base ourselves on is the second result here. In partial fraction decomposition of a rational function, the degree of the numerator fraction, right, the numerator fraction in the decomposition, so of a resulting fraction that's part of the sum or the difference of fractions, may be up to 1 degree less than the degree of the denominator. So that's maybe hard to imagine when just said in words, so let's look at the following example. So here, as an example, we're going to find in part A the partial decomposition of this fraction here, 7x squared minus x plus 2 over x cubed plus x squared plus x plus 1. And then we are going to use that decomposition to evaluate this integral, where the fraction in part A is the integrand of our integral here. So the first thing to do, I am thinking as above that our denominator here is q of x, and q of x can always be factored into linear and irreducible factors, irreducible quadratic factors. So we're going to go ahead and factor that denominator first. We're going to factor by grouping, and we'll see out of the first one we can pull out x squared. That leaves us x plus 1, which is the same as the end of the expression. And then a second common factor step gives us x plus 1 over times x squared plus 1. I said those backwards, but there you go. So we are going to decompose this fraction, which means we have to set up our decomposition. And this is where we are going to use the second result here that tells us that the degree of the numerator can be up to 1 degree less than the denominator. So I am taking each of these factors here. I have got my x plus 1. X plus 1 is right there. X plus 1 has a degree of 1, right? That's x to the 1. And so when I look at the degree of the numerator, that is like having an x to the 0 there. That is 1 degree less. That is 1 degree less, a fact that we just used previously without thinking much about it. Now, here is where the result actually ends up by changing things a little bit. The second factor, x squared plus 1. X squared plus 1, well, x squared plus 1 has a degree of 2. A degree of 2, which means that the numerator of that fraction has to be, or can be, it doesn't have to be, it could be degree 0 or degree 1. So we have to allow for the most general possibility. Degree 1 would be the x here, but there could also be a constant term, right? X to the 0. And so a irreducible quadratic term will always have a linear numerator in the setup. Now it might very well be, it could be that b is equal to 0. That might happen. Or you might have c is equal to 0. That could happen. But you do not know to start with. You do not know. And so to be the most general that you can, to set up the decomposition and solve for these constants, when you have an irreducible quadratic in your denominator, your numerator will be a linear term. Okay, that is what this second result here, that is what that result is telling us. So now that we have the setup, well, the rest of it is pretty much like we have done previously. We want to solve for these constants. Now we don't have just two constants because we have two fractions. We have three constants, a, b, and c, to solve for. So we do exactly like we would have done previously. We pretend that we were putting these things back on a common denominator. So you would have a times x squared plus 1 plus bx plus c times the other denominator, x plus 1, all of that over the same x cubed plus x squared plus x plus 1. If the numerator of this fraction, if the denominator of this fraction and of this fraction are equal, then the numerators must be equal. So it's the same logic as in the simple case, but we have more constants to solve for now. So we've got a, b, and c to solve for. I am going to use a mix and match method. I'm going to start with some magic values, and then I am still going to have to expand after to get the last constant. So I'm going to look at it, x is equal to minus 1. X is equal to minus 1 is not randomly chosen. It makes this term go to 0, which blanks out all of this. And if I plug in x equals minus 1 on the left and on the right, I will be able to solve and see that a is equal to 5. I will also choose to plug in x is equal to 0. X is equal to 0 is going to block out the b, right? And so I will get, when I plug in x equals to 0 everywhere, 2 is equal to a plus c, but I already have the value of a, so I'll plug that in, and then I can solve and see that c will be minus 3. Now, that still leaves b to solve for, and there is no magic value of b that will make it easy to solve. Now, actually, some people might say, well, go ahead, plug in another value anyway, and you could. You could plug in x equals 1 if you wanted to, and you would get an equation for b. What I am choosing to do is to expand like we would previously have expanded in our system of equations method, but I am plugging in the values of a and c. I expand and collect the coefficients of the square, the linear, and the constant term. And then I compare. It doesn't matter which one I compare. They would all give me the same value of b, so I have chosen to take the coefficient of the square and the coefficient of the square. So if 7 is 5 plus b, then b is 2. Right? So there's a mix and match method. You could do this all systems of equations. There's more than one way of solving for those constants. But whatever you choose as your method, you will get that your fraction decomposes into 5 over x plus 1 plus 2x minus 3 over x squared plus 1. That was part A. Part A asked us to find the partial fraction decomposition of this fraction. Part B says, now evaluate. So now if we evaluate, right, the antiderivative that we are asked to find, this fraction can be rewritten as the sum of these two fractions over here. Then we can rewrite our integrand as the sum of those two, and then split the integral up, and you will see that each part leads to a fraction, leads to an antiderivative that you know how to do. This one here is done by a mini substitution, right? The idea would be to let u equal x plus 1. This one here is also done by a little substitution. You would let v equal x squared plus 1. And the last one, well, the last one is just a beautiful arctan, not even one of the complicated arctan formulas where you have to complete the square or nothing. No, it's the pure and simple arctan formula. And so anti-differentiating after the partial fraction decomposition is actually fairly simple. Now, at the beginning of the video, I promised you that there would be 3 results about partial fractions that we would be using, and here is the third one. And the third one has to do about repeated factors. So if any factor, whether it's linear or irreducible, in the denominator, if it appears to the nth power, any factor that appears to some power of n may give rise up to n fractions, right? N different fractions, each increasing in power from 1 to n. Again, the words don't really do this justice. Let's look at an example. If we had a rational function like this, and I've factored out some other stuff here, but let's imagine that we ended up with a repeated x squared plus 1 to the 4th power. In other words, I'm thinking that the n is 4, which means that in the decomposition, there may be up to 4 fractions that come out from this single factor, right? There can be other, in my decomposition from this q of x, there might be other terms here that I've just written with a dot, 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 but with our x squared plus 4, there can be 1, 2, 3, 4 possible fractions, and each of those increasing in power from 1 to n. So x squared plus 1 to the 1, x squared plus 1 squared, cubed n to the 4th. And each one of those fractions could potentially have completely different numerators. So each one of those, because it is an irreducible quadratic, x squared plus 1 is irreducible, each one of those has a linear numerator. Each one of those has a linear numerator. Even if this, right, this is, you might say this is the 3rd power, so 1 degree less means a quadratic in the numerator. No. That is a repeated quadratic. And so the fundamental nature of that term is quadratic, and so it is 1 degree less linear in the numerator, but potentially up to 1, 2, 3, 4, 5, 6, 7, 8 different constants, right? So you can get the impression perhaps quickly that this kind of expansion can get very big very fast with repeated factors. So let's look at a couple of examples with these repeated factors. First here, let's consider this fraction. So I have x to the 13 over x squared minus 1 squared times x squared plus x plus 1 times x cubed minus 1 squared. Now we are asked to give the form of the partial fraction decomposition, but not to solve for any constants. So we want to give the form only of what the decomposition would look like. And so the first thing that we want to do is we want to take this denominator here and we want to factor it. So the first here, x squared minus 1 factors into x minus 1 times x plus 1. I've remained or left the square here. You can check that this factor here is irreducible if you do the discriminant. Which is b squared, right? The delta is b squared minus 4ac, which is going to give me 1 minus 4 times 1 times 1. That is a negative value. That is an irreducible quadratic. And then over here, x cubed minus 1 factors into x minus 1 times the same x squared plus x plus 1, and I have again left the square on the outside. If we distribute those powers and collect the like terms together, we're going to have x minus 1 to the fourth, x plus 1 squared, and x squared plus x plus 1 cubed. So in the partial fraction decomposition, we are going to have how many fractions total? Well, here we have 4. A power of 4, I get potentially one fraction per power. So 4 fractions there, 2 fractions there, 3 fractions there, which means I'm going to have 4 plus 2 is 6 plus 3 is 9 fractions. So 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's upsetting. What's gone wrong? Aha! Haha! Look at that. So a 13x plus a 14. I forgot the cubed power of this guy. Okay, there you go. And so I was counting up. And there's my last one. Okay, so there, that's how many fractions. Now you might look at this ahead and you might say, oh, well, what are these things? What are these things? Well, we have to remember that potentially the first step in any partial fraction decomposition is a long division. And if I look at the degree of the numerator, the degree of the numerator is 13. And the degree of the denominator, do we have to expand it all out to figure it out? We do not. We know the highest power that we're going to get from x here is x to the fourth. We know the highest power we're going to get here is x squared. And when we cube a square, we know the highest power that we're going to get here is x to the sixth, which means that the highest power in the denominator, the highest power is going to be, well, sum those together, is going to be 12. And so we are going to be dividing a 13-degree polynomial by a 12-degree polynomial, and what is the missing degree? We would be multiplying by 1, right? X to the 1 and x to the 12. 12 plus 1 is 13. There could be a x to the 1 term, there could be some constant, we don't know what there is, and there could be some constant here. So these first two terms come from the long division. Now, let's go and look at each of the factors. So the first factor here, x minus 1 to the fourth. X minus 1 to the fourth. So I have x minus 1 squared, cubed to the fourth. Increasing powers. Those are linear, and so there are potentially just single constants up there. I say potentially because they could be 0, but they are just degree 0 or constants here. Next is x plus 1 squared. So x plus 1 squared. No x plus 1 cubed because the power is only 2. Linear, so again, 1 degree lower. Lastly, and this is the one that I had forgotten earlier, we have x squared plus x plus 1 cubed. So I need it to the first power, to the second power, and to the third power. This is an irreducible quadratic, and so the degree of the numerator will be 1, linear, right? X to the 1. And so we've got a 9x plus a 10, again a linear here, and again a linear here. So it's a very good job that we were asked to not to solve, because we would have 14 different constants to solve for if we were going to try. One last example in this video, and that is to use this repeated factor information to evaluate this antiderivative. So let's go ahead and do that. First thing for the partial fraction decomposition is to factor the denominator. And if we do, we see that it factors. First we can pull out an x, then we can do a trinomial factoring, and we get 16 over x times x squared plus 4 squared, a repeated factor. So we need, over the x, we need a simple constant, a over x. Over the x squared plus 4 and the x squared plus 4 squared, we need linear terms. And so we have a through e, we have 5 constants to solve for. So we are going to do the exact same thing. We're going to multiply up and compare the numerators. And so 16 has to be equal to all of this. The magic value, there's a one magic value which will clean things up beautifully, and that is here, if I take x equals 0, those last two terms go away, and I get 16 is equal to 16a, so a is 1. The last, you can continue doing magic values if you want to, and you will still get systems of equations. Nothing will be simple as the first x equals 0. So I am going to choose to expand and collect. So I do all of this. This is the expanding and collecting. And I get 16 is equal to all of this. And I compare the powers. I compare the coefficients. The coefficient on the left-hand side of x to the fourth is 0. On the right, it's a plus b, and so on and so forth. The coefficient of x cubed is 0. On the right, it's c. The coefficient of x squared is 0. On the right, it's 8a plus 4b plus d. On the left, the coefficient of x is 0. On the right, it's 4c plus e. And the last one, 16a is 16, which incidentally gives us a equals 1, which we already knew. But this big old system of equations actually is not that bad to solve. If I know a equals 1, then I can come up here and I get b is minus 1. If I know the values of a and b, that lets me solve for d. And if I go ahead and do that, d is minus 4. If c is 0, well then e had better be 0, and well, that's it. So this is the integral that we were asked to solve. We replace it by its partial fraction decomposition, which turns out to be this. If I plug back in the a, b, c, d, and e from up above, I get the antiderivative of 1 over x minus x over x squared plus 4 minus 4x over x squared plus 4 squared. Little anti-differentiations in each, little u substitutions. The first one and the second one being the exact same substitution, incidentally, will lead to different derivatives, antiderivatives, because of the powers. I get the absolute value, the ln of the absolute value of x here. Here, this is already positive, so I don't have the absolute values, but this will give me minus 1/2 the ln of x squared plus 4, and this is a power rule. Right, we have two different things going on with the same substitution. We get a log rule and a power rule plus c. So all of that to anti-differentiate what seems as a rather innocuous little rational function, but because it has a repeated power, the complexity of it grows substantially.